Hey, folks, for this discussion, we're going to talk about energy in simple harmonic motion. And if you take a moment to pause the video and just sketch the little diagram I have over here, all it is a mass on a spring bobbing up and down an amplitude A from equilibrium. All right, so the first thing I'll mention here is when you have a problem like this, uh, you get to ignore gravitational potential energy if you call equilibrium zero position. Now, I do have a sheet I'll link that mathematically shows why that is, that we can ignore gravitational potential energy. But for this discussion, I'm just going to say that you get to do that. You get to ignore MGH. So that's gone. So the only other types of energy left in this system are kinetic and potential, uh, spring potential energy. So when you're at the very top or the very bottom, you only have elastic potential energy. When you're racing through equilibrium, you only have kinetic energy. So the energy goes from elastic to elastic, and then back to kinetic and back to elastic, etc. Okay, so the energy toggles back and forth. As a reminder, elastic potential energy is 1/2 kx squared, and kinetic energy is 1/2 mass velocity squared. The maximum potential energy, so UE max, would be 1/2 k a squared. And the kinetic energy max would be 1/2 m, and I'll call it V naught squared, V naught being what's the velocity when you're passing equilibrium, okay? The total energy would be either or of those. It's either 1/2 k a squared or it's 1/2 m v naught squared. In other words, if you are at equilibrium, you only have kinetic energy. If you are at one end of the motion, you only have elastic potential energy. So it's either or. If you're somewhere in between, you're going to have a little elastic and a little kinetic, but those will add to either this or this. And which one you add them to just depends on which one you got more information for. Okay. So, for example, let's say you have a problem where before I do that, let me just say this. So E total is equal to the sum of the elastic potential energy plus the kinetic energy. And then you can put either this or this over there, depending on which one you got more information for. Okay. Now, having said that, let's say I didn't give any numbers on this, but let's say I gave you that the mass of the block is m and the spring constant's k, and you displace it in amplitude a. One thing you'll see in the book is they'll give you an equation for velocity that depends on displacement x from equilibrium. Let's calculate that without numbers, okay? So the total energy, in this case, I'll use the 1/2 k a squared. So let's say you stretch the spring a distance a and you let it go, okay? Well, that's going to be equal to 1/2 k x squared plus 1/2 mv squared at any other point in the motion, all right? So what's the velocity as a function of x? Well, you can cancel the halves out, right? And we're going to solve for velocity, okay? So what would you get? So I'll write the mv squared by itself. Well, that would equal ka squared minus kx squared, right? And then you would divide both sides by m, okay? And then you square root, and you get the following. You get the square root of k over m. You can factor out the k over m, and you get a squared minus x squared. Now, the book will go further, and if you recall from the previous discussions, k over m, well, that's the angular frequency omega. So they might write this down for you. I would actually prefer that you don't use that equation from scratch. I would rather you use conservation of energy, okay, and actually write this stuff down, okay? Now, having said that, let's try an example. So let's say this is your example, And let's say I gave you the following numerical stuff. Let's say the amplitude was 10 centimeters. Let's say the mass of the bob was 5 kilograms. And let's say it was a really slow system. The tension or the period of oscillation is 4 seconds. So that's pretty slow, okay? But let's say that I gave you that data about that mass bobbing up and down, that spring. And I asked you for the following. What's the total energy of the system? And what's the max velocity of the system when it's going through equilibrium, okay? So in order to do this, the first thing you're going to have to do is, there's a couple ways you could do this. I will find omega first. Omega is 2 pi over the period, which is 2 pi over 4, which is pi over 2, okay? That would be radians per second. We know that Vmax is A times omega. Okay, and we have both those numbers now, right? Now, A, if you make that into meters, that would be 0.1. 10 centimeters is 0.1 meters, and omega is pi over 2. And this would be equal to pi over 20 meters per second. So that would be your max velocity. Now, by the way, that's pretty small. It's only like 0.15 meters per second, or about 0.3 miles an hour. So that's one way to do this. And then from that, we can figure out the total energy of the system. Now, for the total energy, now I know that the max velocity, so I'm going to use the 1/2 mv naught. So in other words, when the thing is here at equilibrium, all its energy is kinetic. Let's calculate that kinetic energy. That is our total energy. So the total, the max kinetic energy, I'll put max there, is 1/2 mv naught squared, which is 1/2 times 5 times, and I'll leave it as pi over 20. It's kind of cool, squared. And if you do a little math, you get pi squared over 160 joules. Okay, which is a pretty small. It's much less than 1 joule of energy. So your system sure isn't moving very fast. The one last thing that I actually would like to find is a spring constant, okay, which is little k. Okay, so big K is kinetic energy, little k is spring constant. Okay, so how do we find the spring constant? Well, there's several ways to do that. One way to do that is to say, okay, the kinetic energy max at equilibrium will equal the potential energy max at one end. So we have 1/2 mv naught squared equals 1/2 k a squared. The halves drop out. We're trying to solve for that spring constant, which would be mv naught squared over a squared, which would be 5 times v naught squared, so that'd be pi over 20 squared, divided by a squared, which would be 0.1 squared. And I don't know, you'd get some kind of number. Okay, I'll try to do this. I don't have this written out, but it'd be 5 times pi squared. 0.1 squared is 0.01. You flip it over, it becomes 100. And then you get the 20 squared there, that becomes a 400. Oh, this is not bad. 500 over 400, you get 5 pi squared over 4. So that would be your spring constant value, and that would be newtons per meter. Okay. So there you go. Now, other things that you can do with a problem like this is, let's say I ask you for the velocity here, 5 centimeters from equilibrium, which is halfway between equilibrium and the max displacement of the mass. Okay. Well, we know our total energy is pi squared over 160. So we know that E total is pi squared over 160. Well, you would just set that equal to 1/2 mv squared plus 1/2 k x squared. Okay. So in this case, we'd have pi squared over 160 equals 1/2. The mass is 5. I'm trying to find the velocity at the 5 centimeter mark. And then plus 1/2, we just figured out k, it's 5 pi squared over 4. And then x squared that's 5. I'm telling you that's 5 centimeters, so that'd be 0.05 squared. And you can now solve this for the velocity at that point. that velocity would be less than the velocity of pi over 20, whatever. So whatever number you get here better be less than pi over 20 because you're not at equilibrium. So you'd get something smaller than pi over 120. I don't think we need to solve that out, but if you plug it in the calculator, or if you really get ambitious, you can kind of leave it in terms of pi and see what you get. But there you go. So that's an example of using conservation of energy to solve for a velocity of an object somewhere. And again, all we're doing here is using conservation of energy. We've talked about this before, but now we're using it for a specific system of a mass bobbing up and down in a spring. Okay. Also, again, another big takeaway here is you can ignore gravitational potential energy. You don't have to worry about MGH if you call 0 the equilibrium position. In other words, you say this point is x equals 0 for the spring. Okay. So I hope those examples were helpful, and thank you very much.